In theory, this is going to work. We talked about the electron existing, so if we picked hydrogen, we have a single electron around our hydrogen atom.
What chapter is this?
This is chapter 4.
Okay, so
Okay. We give it a cattle prod, so we pump tons of electricity into this. That causes the electron to jump to a higher orbital. Okay? So that blue thing is now a cattle prod. Okay? For those of you taking notes, C-A-T-T-L-E. It's just kind of a joke, but whatever. Our electron's now at a higher energy state. Okay? That higher energy state is so high it does not want to be there, so it is going to relax back down. But we can't create or destroy energy. That had to go somewhere. Okay? We got the energy to make it jump through the cattle prod. For it to go back down, that energy has to be released somehow. Okay? That energy is released as part of the electromagnetic spectrum, okay? Which can be represented as E for energy. Capital E, lowercase e would be electron. Okay? We could also write it as H nu, which is the formula for energy. We could also write it as light. Okay? The most appropriate ways to represent it would be that E or the H nu. The light one's a little bit questionable. That light one is tending to imply visible light. This jump, or that gap in energy there, does not have to be visible light. Why do we reference it then as visible light?
It makes up everything we see.
In theory, this works. That's what we saw. Okay. In the emission line spectrum, we're seeing those colors of light. Those match transitions through the orbitals. Okay? So if we go through and just look at this system, we could have an electron jump from there to there, right? We could also have an electron jump from here to here. Is there another one? Yes, there's another one. Can't jump back, okay, because that's putting energy in. We're talking about here emitting light.
3 to 2. Well, 3 to 2.
I could do 3 to 2. Each of those are now corresponding to a different energy. How would we see that energy? That would be the visible light. Okay? That's what those transitions are referencing. Okay? For hydrogen, we said there were 3. Well, conveniently here, we're showing 3 different jumps. What were the 3 different colors for hydrogen? Okay. We had our purple, we had our red, and then we had... Wow, sliders is not what I wanted. We had like a blue-green, which I don't really have an option of, so we're just going to call it blue. We had 3 different colors of light that could come out for our hydrogen atom. Let's make the assumption, just the assumption, because it's entirely false, but let's say the assumption, this is our hydrogen atom. Okay? Which transition corresponds to which color?
Highest energy furthest.
Okay?
As the purple. 3 to 1.
So we clean that up a little bit. Which ones are purple? The third, 3 to 1. Okay, why 3 to 1? That is the biggest jump. Okay, so that one should be nice and easy to pick out. Does everybody kind of see what's going on with that? Your biggest jump, highest energy. 3 to 1. Now we run into the challenge, though. How do we decide blue versus red?
3 to 2. Play the video game. Oh.
3 to 2 or 2 to 1? Both of them are only making one jump.
What is the distance?
Okay. One of the things that we haven't addressed is what is the energy of each of these orbitals. Okay? And what you'll notice here is that the distance between each of those orbitals is different. And as we get further away, it's a smaller and smaller jump out. Okay? We can sort of address that. Ultimately, you just need to know that that is the truth, that that's how it works. The gaps get smaller. What does that mean for these last two transitions? Which of those is the larger jump? 2 to 1 is the larger jump. Which is higher in energy, blue or red? Blue, which means? That's our 2 to 1. This would be our 3 to 2.
So the blue one has more energy?
Is a larger energy jump. 2 to 1 is a larger energy jump than 3 to 2. Okay? That can be kind of hard to see on this circle, so what we could do is kind of spin it on its head. If we looked at this as energy, here's our nucleus. That says nucleus. There's the first one. Where's number 2? Well, right there. Where's number 3? Higher, but notice the gap here is different. Everybody see that? Mm-hmm. That same thing is being represented in this orbit diagram. Okay, with the circles. Everybody kind of see it? Okay. That is a very important thing to observe. It's also one of the more challenging aspects when it comes to questions that could be asked. You won't get asked those unless you move into 151.
So the electrons aren't going to be anywhere else other than in these 3 orbits?
The electrons are only allowed to exist in an orbit.
Okay.
Yes. And one of the things I want to change there is we want to step away from the term orbit, because orbit makes us think a circle. These aren't circles. Okay? This isn't just, well, I'm spinning around in this giant circle. It's not that at all. Okay? It's an orbital. And you're like, well, what's the difference? An orbital doesn't have to move in a circle. Okay? And that's where we get a slight difference here. We'll look at what those orbitals look like, and it messes with our understanding of this picture. Okay? Because the orbitals are probability shapes, and that just makes things really weird to deal with. Okay, I think there was a hand in the back first. Yeah.
What does it mean? Oh, they get smaller as they go out.
They will always get less further away. Okay? As far as smaller, that is kind of a weird statement, because if you ask bigger versus smaller circles. Yeah.
When the electrons are jumping, are they creating energy or are they just emitting?
So let's reference the energy with our electrons jumping. Okay? If we think about jumping, let's wake up the people downstairs. If I were to jump, what happens? Up and down. There's 2 actions. Both of those have different things on it. I have to put energy in to jump up. Do I have to put energy in to jump down? No, it's just fall. Okay. Same thing's going to happen here. For an electron to jump up, to go from that first energy up to a second or up to that third, I have to put energy in. Okay? It turns out the energy I put in can come from a cattle prod, effectively a cattle prod. Okay? We could also use light to do that. And that actually explains why we see color.
And the light it emits is,
the light that it emits, so we've got the jump up. Okay, this is the up direction, if you will. Okay, the jump down is now coming back the other direction. Okay, so in the jump up, what has to happen? To go up, I have to put energy in. What light am I going to see? And now we're like, I'm hearing some people saying none. We're talking about light going into the sample. If it's going into the sample, is it making it into our eyes? No, so we don't see it. Okay? When are we going to see the light? When the light comes out of our sample, that's the jump down. Kind of, sort of? Okay. I'm nervous that you're going to push some questions that are going to make that a lot worse. But
No, just simplify some.
okay, go for it.
So when you jump, can you jump 1 to 3, or is it it have to go 1, 2, 3?
Okay.
And then you go back?
When you jump, is there an order behind how you jump? Okay. Can you jump from 1 to 2 and then 2 to 3? Or do you jump 1 to 3? Is there a rule that says which one is correct? Okay. When you're going up the stairs, is there a rule to say you can only go up one step at a time? No. See those weird psychopaths like going like 4 steps at a time, right? Okay. They have to put in a lot more energy. That's how they're able to do it. Okay? For us normal mortals, we can't make that jump. Okay? We don't have that energy supply. The same thing's happening here. The jumps that are going to happen match the energy that's put in. Okay? You would probably jump from the first to the fourth step pretty well if we put enough voltage in behind you. That's what's happening with our electrons. Okay? Kind of makes sense? Okay. So there's no rule to say how far, how many jumps you can make going up. There's no rule to say how many jumps you have to make going down. Okay? All of those are possibilities. That does not mean we will see all of those. Why not?
Is there cases where there's other sets of rules for different?
Same rules. Why would we not see a jump?
It's because it's a type of light.
Getting at the right idea, remember the jump is corresponding to an energy. The reason we see that energy is because that energy matches our visible spectrum, what we can see. Is there parts of the electromagnetic spectrum that we cannot see? Yes. Some of these jumps are so high energy as a release that that light is now in the ultraviolet region. We can't see it. So if we looked at our atomic line spectrum, we're going to be like, well, where is it? It's not there. Well, the atomic line spectrum is only the visible region. Okay? We can have jumps that exceed the energy that we're allowed to see or that we're capable of seeing. By that same token, there could be a jump that is so small of the electron that we can't see it because now that jump releases so little energy that our eyes don't respond to it. Okay? Kind of makes sense? Okay. Is it possible to, so let's clear all that away. Here's my electron. Instead of giving it, say to make this jump, I need 6 volts. Doesn't matter. 6 volts to make that jump. What if I give the electron 3 volts?
It'll go slowly?
It can't do it. Okay? It literally won't move. Okay? It's going to stay stuck at that same energy level. 3 volts would theoretically take it somewhere halfway in between. The electron cannot exist there. It can only exist at those independent orbitals, which we will reference as energy levels.
Why can't it exist in between?
So the reasons behind why it can't exist in between have to do with, ultimately, this guy, Niels Bohr, looking at where electrons are allowed to exist. Okay? And this is when we talk about crazy weird stuff, and you're like, science just does weird stuff. This is why Marvel can be like, oh, everybody died. Quantum, and everything works. Okay? Why? Because that's what quantum chemistry does. Okay? This electron can jump from this orbital to this orbital if it has that energy, but at the same time not pass through that space. So let's just kind of put this out there. What we're saying is that if I was an electron, I could make it from here to the door, but not occupy any of the space in between. How does that happen? Quantum. Okay? And it is pretty fascinating. Okay? There's a lot of physics and calculations that go behind that, and ultimately what we're looking at is probabilities for how these things can move, and we start to run into all sorts of weird things. That is very difficult for our brain to process because we don't exist at the quantum level. We can't see or interact with those things. We have no basis for experience. Okay? So what we do have the ability to do is to test these theories and be like, well, if this was true, then this can happen. Oh crap, it did. That must mean my statement was true. Okay? And that's one of the powerful things behind the mathematics of quantum chemistry. Okay? What you end up seeing in Chem 130 and 151 is the end result of all of the hardcore mathematics and physics that went into it. The mathematics and physics is absolutely fascinating, and I have never sat in a more gorgeous lecture than I have ever been in, than in a quantum physics class where they actually solved everything through. It was amazing. Then I had to take a test in it, and I didn't feel it was so amazing. Okay? So it is an absolutely fascinating subject of study. What you're looking at are the end conclusions. Why do we not dig into the mathematics and the physics behind it? Well, how much mathematics and physics backgrounds do you have? None. So what we're going to do is instead look to the conclusions, because from those conclusions, we can make a lot of sweeping statements about how these molecules react and interact with the world. Okay? That's the part that's cool. Okay? Which unfortunately means we kind of just have to not ask the question, why can't it exist there? Okay? Which does suck. Okay? And there's no answer I can give you that's going to be acceptable. Literally. For multiple reasons. Like, I don't have a good answer. Okay? So, we have these orbitals, which I'm going to refer to as energy levels instead of orbitals at this point. Okay? And we'll see why later today, why I want to reference them as energy levels. You'll notice I'm also making a pretty big break from the book. This slide, or this image, came directly from the book, and what do they call them? Orbits, which is, again, a misnomer. This is why if you look at little kids like art fair projects on chemistry, they show these big circle things with all the pennies like stuck in, like, oh, look at these pretty orbitals, and it's a load of freaking BS. Okay? But it's a hand-wavy enough approximation that we just kind of accept it. And the people that know better just kind of die a little bit inside. But, you know, they're chemists. It's okay.
So you're saying the communication used is not accurate, but people basically get the idea?
Yeah. Okay. This quantum concept, okay, brings in some new words. So we got the quantum concept. And really what the quantum concept is saying is that we have discrete or defined energy values, kind of like stairs. Okay? When you go up the stairs, can you exist at a step and a half?
Yes.
At a step and a half. Okay? You're telling, don't do that. I knew you were going to do that. Okay, let's just let it do its thing. Okay, there's step 1, there's step 2, there's step 3, right? Everybody see that?
Yeah.
Okay. If I was to draw a person at step 1, use big feet. There's a person at step 1. If I draw a person at step 2, don't make fun of my peoples. Okay. There's a person at step 2. Am I allowed to draw a person standing at step 1.5? You can't stand at a step 1.5. You can pass through it to step 1, right? Or if you put in more energy, you could advance to step 2. You can't exist at a step 1.5. There's literally nothing there to hold you. For those of you like, I can levitate, knock it off. Okay? You can't exist there. But if I look at a ramp that covers that exact same distance, could I stand at that same height on the ramp? Yes. The ramp is a continuous system. Stairs or steps are discrete. Okay?
So
Kind of makes sense?
All matter is on basically is on the slope, except for electrons, which are on the stairs.
Yeah. I think I can accept that one. And I'm a little bit irritated because this thing just locked up on me. But we don't need that picture, so we'll just talk through it. There's the picture on that slide. Okay? So what we're talking about is our electrons and orbits are quantum related. And as quantum, they exist at discrete energy levels. That's all due to Niels Bohr. Okay? Ramps are not discrete. Those are a continuous spectrum. Okay? Let's use our understanding of light and what we've talked about with light to represent this continuous and discrete system. If we'd put hydrogen in and we got purple light, and we thought that our electrons could exist anywhere as a continuous space, they could exist at a bunch of different energy levels within the purple area. Which would mean when we look at the atomic spectrum for hydrogen, what should we see?
Blur.
A blur where?
In that color region.
In the purple region. Okay. Do we see that as the end result when we pump 20,000 volts into our hydrogen sample? No. Instead, what we see are these lines. What are those lines? The discrete energy levels. Our atomic line spectrum are examples of discrete energy levels. A rainbow spectrum is an example of the continuous energy system. Kind of make sense?
Can you say that again about what the quantum concept is?
So all the quantum concept is saying that we have distinct energies. Okay?
Like light does, or everything has distinct energies?
Our electrons exist at discrete energies. To transition between those different energies requires a quantum. So when we talk about quantum physics, what are we referencing?
Light. Energy.
The energy levels of our electrons. Okay, where the electrons can exist. Okay, that's what we're referencing when we're talking about quantum. How do we know that that exists? Because of the energy lines that we're seeing in our atomic line spectrum. Okay, so what we're doing, or what we did, is we came up with a theory. We tested the theory. We had a sea of positives with just a bunch of floating chunks of electrons inside it. Who did that? Don't worry, the test is in a couple weeks. You got some time. Thomson was wrong. Who proved him wrong? No. His student. Good. Unfortunately, student is not one of your answer choices. What was his experiment?
That one where he weighed, he found out the mass of.
No. Gold foil. Rutherford disproves Thomson's model using the gold foil experiment, aiming a shotgun at a piece of paper and having the bullets bounce back and hit you. That was Rutherford. That proved the existence of a nucleus. Okay? At that point, we now know where protons and neutrons exist, but we don't know where our electrons exist. They're just somewhere outside. So what happens? We continue to study. Bohr comes in, looks at the atomic line spectrum, and says, the only reason that makes sense is if our electrons can't just exist everywhere. They have to exist at very specific locations. That's quantum physics. Yeah? Sure is a great way to make me think you understand it.
So how does this relate to time travel?
Okay. No time travel. I'm not doing it. All right? So if we go through and now look at an actual representation for hydrogen, okay, you'll notice that this time they've added some more information. They've put in numbers. Those numbers refer to the different energy levels that are possible for hydrogen. Guess what other elements have those energy levels? All of them. How many energy levels are there? 7. Does anybody see a set of 7 on the periodic table? The periods, also known as the horizontal rows. Hydrogen would be in the first row, lithium, second, third, fourth, fifth, sixth, seventh. 8, 9? No, those were part of 6 and 7. There are 7 rows in the periodic table, corresponding to the 7 energies that an electron can exist at. The periodic table has the electron configurations or the electron locations already mapped out in it. You just have to know that it's there. That's kind of neat. Okay? If we now go through and take a look at the specifics of this one, where did we say we could have jumps from? 2 to 1, 3 to 1, 3 to 2, 4 to 1, 4 to 2, 4 to 3, 5. And I just heard someone say, oh God, that's kind of what I was fishing for. There's a lot of different jumps that could come out of this. Why do I only see 3 different lines? And not for all of those? Those jumps are the only jumps that fall within the visible range of energies. The other jumps are outside the range, so we don't see them. Okay, they are there. Could we use an instrument to pick them up? Yes. Well, it depends which range you want to look at. If you want to look at the ultraviolet range, we have what's known as UV vis spectrometers. UV for ultraviolet, vis for visible spectrometers. Those typically range through the entire ultraviolet spectrum and into the visible. Okay. If you wanted to see the IR, night vision goggles. Okay. That's exactly their purpose, is to pick up those energy transitions. Okay? So, if we go through and look, we reference them always going down to the 1. For the hydrogen, do they go back to the 1? No, they actually all stop at the 2nd energy level. Why? That's just where that energy matched to get the light that we see. That's it. The other transitions are not part of the visible spectrum. Before you get too well, but I'm pretty sure the distance between 2 and 1 is roughly the same as that distance between 3 and 2. This is not to scale. Don't do that. Okay? This is just to give you a rough idea and approximation of what's happening within it. We're choosing to ignore those other transitions and ignore that, if we did some kind of scale stuff, we'd see that. They did attempt to do some scale. How do you know they attempted to do some scaling?
You can see the differences.
We do see differences in those energies. As we move up, the gaps get smaller. The gap between 3 and 2 is relatively small, which would mean what kind of energy? Small energy, high energy? Small energy, which would correspond to what color light? Red. Oh, there it is. Look at that line. If we look at the jump between 4 to 2, is that larger or smaller than the 3 to 2? Larger, which means it should be higher in energy. How much higher in energy? Who the hell knows? We don't have the scale. Because we have hydrogen here, we can make the assumption that that's the alignment. Make sense?
Yep.
Last one, 5 to 2, biggest jump, most energy, violet. Cool? Okay. And I'm hoping the computer is caught up with me. The next big part that comes out of this is if we go through and do every different element, you notice we get a whole bunch of different bands coming out of these. Why would they all change? Don't they all have the exact same energy levels? They all have 7 energy levels, but each of those energy levels is different. Why are they different?
Why would they? Different properties. Because you need a different amount of energy to pull them away from the protons that are pulling them in.
What changes as I go from, say, hydrogen to helium? I change the protons. More protons means that first energy level gets sucked in a little bit tighter. The closer it is to the nucleus, the lower in energy it becomes. Every time we change an atom, the entire model changes. Okay? So when you want to go through and look at the actual quantum behind this, and you take a quantum physics class, everything they talk about is for a hydrogen atom. They go, well, what would happen if a hydrogen atom had 4 electrons? Well, this is what would happen. Hydrogen will never have 4 electrons. Why did we pick hydrogen?
Everything's based off.
Because if we threw in a different element, it changes the nucleus, which changes the energy, which changes the entire model system. And the whole thing gets thrown out. And you have to start from scratch. So we built our model with hydrogen as the simplest, and then we compare up while still kind of maintaining that same core structure. And it allows us to make a lot of those simplifications. The same calculations we do for hydrogen, just by scaling up to helium, can take a computer from minutes to hours. Okay? That's a pretty huge deal. All we did was add a proton and an electron and 2 neutrons. But relatively simple change, and we're seeing a large difference in it. Okay, so every time we change our element, we're changing those energy levels a little bit, which means the jumps between them change, which means the line spectrum change. What's cool about that is I can now look at a line spectrum, say of a distant sun, and say, well, I know that that sun is made up of X percentage hydrogen, X percentage helium, X percentage iron. What? Why can I do that? I take the light that's coming from the sun, I put it through a prism, and I look at the atomic line spectrum coming out of it. I can then desegregate that information, vary it based off of intensities, and I can now determine the exact composition of a far distant sun. That's insane. That's astronomy.
Wasn't that discovered by that woman in the system?
I wish I could answer that question. So let's just say yes.
I'll find the answer for that.
All right? So these generate atomic fingerprints. An atomic line spectrum can be referred to as an atomic fingerprint because no other element has the exact same fingerprint. So I can look at them and define what element I've got. That's kind of cool. Does that mean you should go through and memorize the atomic fingerprints? No. Good answer. No, don't do that. I just want you to recognize that you can use them as fingerprints. Okay? Are there easier ways to distinguish, say, hydrogen from lithium?
Yes.
Yeah, what's that?
Atomic number.
Could do atomic number.
Mass.
Atomic mass.
Based on what criteria? But so we can see up there?
Based on what criteria? That's a good addition. Would have been nice if Greg had talked about criteria today. Oh, well.
I showed up twice. Now I feel like I cheated you guys. We'll get there.
What's the difference between hydrogen and lithium? Symbol, protons, neutrons, electrons, sure.
Different everything.
It's mass.
Lithium is a metal. Hydrogen's a nonmetal. Lithium's a solid. Hydrogen's a gas. You guys pointed out very valid differences. That's awesome. Metal, solid versus nonmetal gas. That's kind of like a big one. You should probably do that one first. Okay? So before dealing with the quantitative measurements, which is good, we have qualitative measurements that allowed us to tell the difference quicker. Okay? Kind of, sort of?
Sure.
If yes, say yes.
So, electron ohms. Okay? This is the big reason, and this is where it's going to kind of explode out and become challenging to deal with. We have our different energy levels. Okay? Our nucleus isn't on this slide because I wanted to show all the energy levels for our electrons. Our nucleus is somewhere in the floor. Okay? Because our first energy level is a fairly decent distance away. Okay? Let's just say we pull the electron. Is there an upper bound to where the electron could be? So we're hearing 7th energy level. I didn't ask about energy level. Here's a proton, here's an electron. I start to pull it away. Is there an upper bound? I don't know. Is there a point at which the electron is no longer associated with the nucleus?
When introduced to another
Okay. We could say bring in another atom. You're making it more difficult. I don't want another atom. Is there a point where that electron is no longer associated with that nucleus? Yes. Where is the electron?
In between levels?
It's no longer associated with the nucleus, so it can't be at an energy level. Where is it?
Yeah, in the quantum realm.
We've actually already talked about it. What else are what else is around that atom?
Empty space. Other atoms.
Empty space. There's no other atoms, because remember, we're trying to simplify it. There's empty space. So I could say my maximum is empty space. And I'm going to have a problem with saying empty space. What is that problem?
It's an oxymoron. I don't know.
That's way too many letters. What happens if there's nothing around? What do I have?
Zero. Vacuum? E.
One.
Did I get it right? Please.
A vacuum? Which brings in the next issue. Why am I not going to like vacuum?
Too long.
I don't know how to spell vacuum. So we just call it vac. And by we, I mean me. Okay. Our max energy is the vacuum. We can't have an atom associated or an electron associated with the nucleus once we've achieved the vacuum. So that's that maximum point. Okay? We could go through and try and break these as equal energies, and you'll find it's kind of difficult to stack those in there. If that was the case, if they were all at equal energies, we don't see the weird atomic line spectrum we've got. Okay? Which is why what we end up getting instead is something along these lines. And if we look kind of carefully there, we should, in theory, see 1, 2, 3, 4, 5, 6, 7, and then that last one is our vacuum. Cool? Mm-hmm. I want to name them.
Greg.
Okay. One option, Greg. See, he's the first one because he teaches English. It's the core content that covers everything.
He named his son Corbin because we hadn't got to know each other well enough yet. So that second one, no, that's funny.
Fifth element, actually, if we're going to go there. We could Greg, Stan, Bubba, Joe Bob, Boomer. Okay? We could come up with those names. Okay? What's the problem with naming them like that?
They're all male.
Touche.
Fair balance at least.
Myra.
There's no way to quantify their relationships.
So it could be an interpretation information. What would be the relationship between... This gets an extra funny question this way.
Myra and Daisy.
What is the relationship between Myra and Bob versus Bob and Greg? Myra's closer than Bob. Bob? Yeah. That relation, you'd have to then memorize all of that. I wonder if there was a better way that we could represent those and have those relationships tied to something we already know. You mean 1, 2, 3, 4, 5? Yeah. And you're like, chemists are stupid. This is literally how we do it. Okay? 4 brothers. The eldest brother went through and numbered us all. I was 3. So we go out on vacation. Hey, 3. Get off of that stoop. 3. Give me my soda back. Okay? It makes it easier. You have a way to reference. You even have a hierarchy behind that system. Okay?
Get up to 7.
Okay. It's also kind of frowned upon naming your kids after numbers in general, just so you know before you go that path. But in any case, that's what we've done. Okay? So now let's push this to the next point. Because what are these energy levels? What were these supposed to represent? Distance from the nucleus for what? Why do I care about the distance from the nucleus? It's where the electrons can live. So it's not just distance from the nucleus. It's saying the electron can exist here, 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 here. Okay? Where did the protons all live? In the middle, right? Why do we have neutrons? To stick all the protons together. Once we put all those protons near each other, they would repel away. So like charges repel. How many electrons can I fit in this first energy level? Okay. What's the issue with placing our first electron there? Is there an issue? I don't know what you're referencing. That doesn't matter. My first electron, regardless of what atom, where should I place it? 1. Why? Lowest energy. Where should I place the second electron? With it. What happens when I put 2 like charges near each other? They repel. Am I going to be able to put 2 electrons in the same spot? No. So what happens? Goes to the next one. Anybody see a problem with this theory?
Because it would get too high energy level for it to...
Well, they get closer and closer, yeah. And how many electrons can we account for? 7. We have a few more elements than 7. Just a couple more. So something's missing. Turned out one of those things that's missing is this extra quantum weird thing. Electrons have a spin. Okay? And what's special about that spin is you can put 2 electrons near each other as long as they spin opposite directions. Okay? Those are being like, what the hell does that even mean? This is what it means. I can put my first electron and I can specify that it is spinning up. Right? Because it's a little arrow. Where would my next electron go?
Down.
Spinning down. Where's my next electron go?
I think they can only spin up and down, right?
They can only spin up and down. We only get 2 spin states, which is the other thing. We only get 2 spin states. So we would jump up to the second energy. And then? Cool. That explains another 7 elements.
Yeah.
We're now to 14. So our theory still has holes in it. Okay? And this is where the probability and the mathematics all kind of come in, is in looking at how electrons can exist. What we end up finding is that every time we move up in energy, we add a new type of orbital. Okay? So when we start at the first energy level, I got rid of all the numbers. That was fixed easily. Our first energy level looks like a sphere. There is only one orbital type for the first energy level, and that's it. It's a sphere. When I go up to the second energy level, I get a new type. Okay? Why do I get a new type? Quantum. Sorry. Okay? What happens? Okay? It's not that I just get a new type. I have to copy the type I already had. Okay? We add on knowledge. We don't delete it. So I also get another circle one. But I have to add another one. That other one? Oh, holy Jiminy Christmas. There's a little better. We get a shape like this. What happens when I go up to the third energy level?
You get both of those plus a new shape.
I get both of those plus a new shape. Okay? So copy, copy, new shape. What happens when I go up another energy level? I'm glad I picked yellow for this because this one doesn't really show up, does it? Oh, damn it. Well, I was hoping it didn't show up. Pretty sure I drew that one wrong, too. You get two of these weird four-loby things kind of side by side. Okay? So every time we go up, we get a new orbital type. Okay? Neat. Each of those orbital types, if we run off the same basic pattern, can still hold 2 electrons. I'm not really good at... what was that?
I did the math before. It's 56.
Thanks. We get 56! Awesome! A bigger number than 14. Not 118. Okay? Next layer of quantum. Every one of these orbital types has different orientations. Okay? The orientations really only work as a description on the lower order ones when we're looking at our first and second energy level. And it kind of works for the third. It becomes really confusing for the fourth. Okay? They're different orientations. Okay? So let's think about each of these shapes. If I took this circle and I turned it, would that orientation look different than that one? No. So how many orientations are there for a circle? One. Ta-da! That is my new representation. Okay? Second energy level. I still have that circle, right? How many orientations are possible for a circle? One. What's the next shape?
Figure 8.
If I rotate that, would you know I rotated it?
Yes.
Okay. This one's a little bit hard to see. Remember, we're in 3 dimensions. What we're talking about is taking that dumbbell shape, if you will. You can mirror it, black, red. There's our dumbbell. Okay, the first one I showed here. Can you tell if I rotate it like that?
Yeah.
New orientation, new orbital. New orbital. Don't think too hard. Don't do that. X, Y, Z. There are 3 orientations. Is the Z-axis. Yep. So how do we represent that? And I'm going to delete that X and Y because they just look freaking ugly. 1, 2, 3. What happens when I move up to the third energy level? I get 1. I get 1, 2, 3. How the hell do we do orientations for that one? I wonder if there's a pattern buried in the periodic table that would help me determine that. To get there, we first have to process through the rest. So let's process through the rest. First electron goes where?
In level 1. Level 1.
Is that level 1? Well, did you name those? Well, how the hell do I know where you're telling me to place the electron? Because I'm more of a jerk than you, I'm telling you you need to come up with a naming system for this.
He said one on Greg.
One on Greg? Oh, yeah. Which one is one? Why, when I placed it here, was that not one? That was in 2. Oh, we did have a numbering system, right? We did label that. So when we said that first energy, Mike was just being a pain in the ass because there really was only one place to put it. Where do I put the second one? Up here?
No, next to it. Rotate.
I go next to, remember, each orbital can hold 2. Spin, flip. There it is. When I put in 1 electron, what atom do you think I was referencing? Hydrogen. Which row is hydrogen in on the periodic table? The first row, right? I added a second electron. What atom was I referring to? Helium. How many elements are in the first row?
2.
How many electrons could I fit into the first energy?
2.
That just has to be coincidence, right?
Yeah, it is.
Third electron.
On that first line up,
Lowest form on row 2.
on row 2, first one down.
You guys are having real challenges with language here.
Dang. In 2 first row. Yeah,
We
man.
need a system for this.
I wish we had a better way to represent this. Okay? Why not just tell me it was 2 sphere? Right? As opposed to 2 weird symbol. Weird symbol is a bit of a mouthful, and that's going to become problematic when we move up to the third energy level. Okay? So we need to come up with a better system. Instead of calling it a sphere, we could call it circle. Has the same number of letters, don't count them. Lazy. What is the laziest way to represent sphere? You really want to draw a circle for all of these. Think back to our periodic table of elements. How many of those are circles and stars and shapes and triangles? What is simpler than a circle? We could do a number. A number would be a fantastic idea, except we already have numbers. That's going to be confusing. I want a letter. What letter should I choose to represent sphere? S. I can now refer to that now by a name. Instead of referencing that first one as the first energy level, I can call it first energy level, the S-type orbital. When I move to the second energy to place that first or that third electron in, I'm placing that electron where? The second energy level and the S-type orbital. That's kind of cool. Okay, before we do that, what element did I reference?
Lithium.
Lithium. Which row is lithium in? What energy level did I just move into?
Wow.
For those of you being like, that's totally not cool, do like any other element. We've just established a pattern that works for how many of those elements?
118.
Every single one. The periodic table does that for me? Yes! That's why it's so cool. Yes?
So, how would you word this question like that?
We haven't even gotten to that yet, but we will approach that. Okay? Next electron. Where do I place the next electron?
Next to it.
I don't accept next to it.
2S.
In the 2S.
2S opposite.
Okay? Remember we had the names for the different sections of the periodic table? I'm not about to flip backward and lose all of my work. The first 2 columns I said were named the S block. Remember? We had the alkali and the alkaline earth, and I went through and said these were known as the S block. Why did I refer to them as the S block? When we look at their outermost electrons, where are they going? Into the sphere-type orbital. For every single element in those first 2 columns, their last electron, their outermost electron, goes into an S-type orbital. Will it always be the 2s orbital? No. What's going to dictate the number? Look at the row that you're in on the periodic table. You can reference energy level. How many of you want to draw this? Okay, let's try it a different way. How many of you drew this? That was hard, wasn't it? I would hope the periodic table had that information encoded in it. It does. It's flipped upside down. Right? Next electron. Where does it go? To the next one up. The 2 one. The 2 that looks like that goofy shape. Again, I want another symbol to represent that goofy shape. What symbol do I use? It's P. Why is it P? Because the other letters were already taken. Right? That is the reasoning behind it. So our first electron, or our next electron, will go into a 2p orbital. What element did I just describe? Boron. 1, 2, 3, 4, 5 electrons. If I have neutral boron, 5 electrons, there it is. What's an interesting feature on our periodic table about boron, say in comparison to beryllium and lithium?
It's metal.
It's not actually metal. What is an interesting feature about the difference between beryllium and boron? The beryllium and the boron. It's on the other side. It's on effectively a different page. You mean it's in a different, say, block? Yeah, what did we call that block? Go back and take a look at the notes. The P block. Where did I place that electron? What? Yeah, there it is. You ready for the next one? Yes. Next electron, where does it go? 2p. Okay. Let's do a couple options here. Let's pick orange as our color. Orange or green? Okay. This becomes trickier. When we started down low, our first electron, then our second electron started down here, right? We paired it. Why did we pair it?
You had to.
No more, because they repel each other, so one has to react to the other.
So one could spin the other way. If we had to pair it ultimately, because if we only had one energy level, we didn't get enough electrons. So the mathematics showed us that we were allowed to pair as long as the spin was the other direction. Okay? When we go up here, am I allowed to pair?
No, because no resistance.
What is the resistance to jumping? Putting a single electron here paired versus placing one up here. I have to have the energy to make that jump. When we look at the orange electron versus the green electron, which one would be more happy? The green one. Because it doesn't have to fight with another electron. So we will pair as long as we don't go up in energy. Right? So in this case, we don't go up in energy, so we don't need to pair. We just fill it out singly. Orange is wrong. There's our next electron. Next electron. The last P. Okay, just for a reference, didn't we name each of these things so we'd be extra clear, right? Did I go through and name each of those P orbitals?
2p1.
We could call them 2p1, 2p2, 2p3, which could potentially work. The problem with that,
We're gonna have a lot of p missing.
you'll have a lot of P. Did you set me up for that? We're just a bunch of 5-year-olds. That's just...
We're learners.
Our electrons are up there. I just completely missed the boat. So why would that become confusing? Because I could go through and now reference how many electrons were in each of these. Okay? If I only had one electron in the 2p, what might I call it? 2p1. If that one electron is in the first of the 2p's, then I'd have 2p1, 1?
Right.
Is that 2p11? Okay, that starts to get confusing. Okay? That naming system we don't need to refine. Okay? If you decide that you want to refine it, that is okay. I actually already gave you the coding system for it. These were each labeled off of the axes, x, y, z. I can refer to these as 2px, 2py, and 2pz. We typically do not need to nuance that far into the naming system, okay? But we could. Next electron. Any one of them, down. Next one. Any of the empty ones, down. Any of the empty ones, down. Yeah? Okay. So we're going to try a little bit of fun stuff here. This one, back here. What element did I refer to when I only put electrons into that one? I was in the second energy level, S block. I was looking at beryllium and lithium, right? How many electrons can I fit into the S-type orbital? 2. How many columns are in the S block? S block, columns. 2. The alkali metals and the alkaline earth. Those are our columns. That's just low numbers, random chance. How many electrons could I fit into the P-type orbitals? 6. How many columns in the P block? 6. Interesting. That's starting to look like a pattern. Before I potentially get distracted, let me finish. What happens when we move up to the third energy level? We'll have our S, we'll have our P, and then what do we move up to? Okay, we have that weird goofy shape, right? I don't know why I circled that one. What do we want to name that one? D. Why? We could go back, because quantum's a good answer, we could go back and say, well, Mike's starting to point out that there's patterns here of S blocks and P blocks. What were the 2 remaining blocks? D and F. F has been pulled out, was way, way low in this. We're now at the third energy level. Scandium is much, much closer than our lanthanides. Before you start flipping out the rows, don't flip out at the rows yet. We'll address that bridge in just a second. Okay? How many columns in the D block? 10. How many different orbital orientations are there for a D-type orbital? Hold it.
Say that again?
How many different orientations are there for a D-type orbital? Remember, the S, we said there was 1 orientation. The P, we said there were 3 orientations. And we could kind of hand wave our way through those orientations. As soon as we hit the D orbitals, we can't hand wave those nice orbital orientations. Like, that's just a giant mess. There's no way I'm drawing it. Okay? But what we've established is that the amount of orbitals is embedded in the periodic table. So what I'm asking you to do is to extrapolate what you know about the D block or what you know about the S block and P block, and extrapolate that information out to the D block. So for the S block, how many orbitals were there? 1. With how many columns? 2. For the p block, how many orbitals are there? 3. With how many columns? What's that relationship? You seeing a relationship? 1 became 2, 3 became 6. I now have 10. I want to reverse it. There's 5 orientations. 1, 2, 3, 4, 5 for the 3D. Okay? Absolute truth. That's what it is. We go up to the 4F. So now we jump 4S, 4P, 4D, 4F. How many orientations are possible for the 4F?
7.
Okay? I'm saying a lot of people look towards the board and towards me. Trust me, I'm not giving you the answer. Greg's not giving you the answer either. The periodic table tells it to us. It's the number of columns in the F block, which is 14. Because I can fit 2 electrons per orbital, cut the 14 in half, and I get 7 orientations for the 4F. If I extrapolate this all out, do I now have enough places to explain all the electrons on the periodic table? Yes. Do I have the ability to actually extrapolate to larger atoms? Yes. That's why we're still actively looking for larger atoms. Okay? We have an ability to see that theoretically, according to the mathematics, we can put more electrons in. We can make bigger things. Okay? That's what we're trying to do. Realize what we're trying to do is jam more electrons in up here. What's the problem with putting more electrons in up there? They're so close to the vacuum, they're also so close to each other that they're going to start spitting away from each other out into the vacuum, which means they're becoming increasingly less stable. Okay? When we get that large, it turns out the physics of the electrons become irrelevant, and it becomes the physics of the nucleus that becomes more important. This patterning that we see for electrons actually also exists for the protons. How many of you want to look at that? You guys can take a different class. The rest of you don't need to worry about ordering of the protons. Okay? That's nuclear physicist stuff. Okay? So our periodic table holds this information. That's kind of cool. Yes, back to you. Now that you forgot your question.
So why is helium in the
So if we go through and look at this, hydrogen might have made sense because its electron went into the 1s, so that makes sense to be part of the S block. We've got an interesting question. Helium. Okay. Jeez, people. Tough crowd. Second electron, it goes into the 1s orbital. Why am I placing helium over in the p block? It has to do something with its reactivity. Okay? Remember also that I said our periodic table doesn't do an extra step that a lot of more modern periodic tables actually do. What did I say they did with hydrogen and helium? They separate them away from the bulk of the periodic table because they are so simple that those patterns don't hold true. Okay? So helium and hydrogen aren't really part of S or P. Okay? You will sometimes see helium written right next to hydrogen. What are they trying to emphasize? It's part of the S block. You'll sometimes see hydrogen written right next to helium over here. They aren't part of the friggin' P block, so why would we do that? Why is helium over here? Because it matches the reactivity of the noble gases. Why would we place hydrogen over here? It matches the reactivity of the elements underneath it if it's placed there. Okay? We haven't addressed that reactivity, so don't stress about that yet. Okay? But that is one of those weird things with hydrogen and helium, why they get sometimes floated off of it.
But they're still identified as the S.
They're still part of the S block.
For the sake of the pattern.
Yep. Okay, questions about that? I still got at least 30 seconds. Okay? So, Big things that come out of this. Electron spin, we actually addressed first. It's the last thing when you look at the quantum mechanics. It's the last variable in the quantum mechanics. Okay? We addressed it first because it kind of made sense to show up first. After that, we get orbital types. What were our orbital types? S, P, D, F. Are there more? Yes. Have we gotten there? No. So we don't need to worry about them. Officially, I think it actually goes GH. Okay? After orbital types, we have orientations. The orientations work very well with the S and P block. They become a little bit more questionable the further up we move. We'll look at the D block. It does actually work, sort of. Okay? It gets a little bit more complex. What we are trying to describe is where every single electron exists. And people get mind blown by how, oh my God, that's way too difficult. There's no way I can figure this out. The periodic table has most of that information coded in it. Okay? We have to be able to decode it. That's part of the language of chemistry. Okay? The other thing that I want to add behind this is you've done this before. Have you ever told somebody where you lived?
Yeah.
Did you have to tell them, like, the address number? Like maybe the street or the direction of the street, the city? Okay? This is just an address. It's just in chemistry language. Okay? That's what we're trying to reference, is the existence of those electrons and where they are found. Okay? Just to give you the better pictures for the drawings of these, S, P, and D. You can see the D looks a little bit nicer there. Okay? Orbital orientation, there's only one way you can orient a sphere. The p orbital, you can orient 3 different directions. Those are the axes, x, y, and z. When we get to the d orbitals, notice we've got the axes labeled on there again. There are a total of 5 orientations. See, we take that, okay, and then we turn it a little bit. Now instead of being on the yz plane, it's on the xz plane. It's on the yx plane. That's the, geez, which plane is that on? They're orienting it on the different planes. And then this one is clearly you just kind of turned it, rotated it, centrifuged it, gave it to Homer Simpson, and you were done. Orientations don't work perfectly. Okay? They're artifacts of the mathematics. Be aware of that. Shapes, sphere. Dumbbell, cloverleaf. Thanks for not making me do a little Irish jig. Okay? Those are the names of those shapes. You are responsible for knowing those names of the shapes. When it comes to questions, the questions is really going to come into telling me where, for cobalt, where's its outermost electron. Okay? And we'll address that on Tuesday.
Real fast, if I